Our final topic for 8201 will be how to find the derivatives of sine and cosine, our trig functions. There'll be some simple ones, and of course, there'll be some nutbar ones. Even though we're just looking at trig functions, I want to bring in the term transcendental functions because you will definitely see in future classes working with trig functions, but you might also see e to the power of x and what we call ln x, and these are also transcendental functions. We haven't really gotten into them, and I really won't get into them here, but it's just basically an exponential and the inverse. But I want you to see this word because a lot of things reference the word transcendental, and that's anything that's not a polynomial, right? If it doesn't look like your normal x squared plus 2x plus 5, or use these kind of BEDMAS operations, it's transcendental. We'll start with our sine curve, and here I've drawn it, and of course we're using radians because calculus loves radians, so we can see that it starts at 0, maximum at 90 or pi over 2, back down to 0 at pi, minimum at 270 or 3 pi over 2, and then it completes one cycle at 2 pi, and because it's periodic, we know that it's just going to start over again with exactly the same shape and continue in both the negative and positive x directions, theoretically forever. So this is a great little site, GeoGebra, and if you hit that link, it'll take you to where you can actually run this animation, which is pretty cool. So what I have on here is at point P, I see that the value of sine x is 0, but they've added in a little red line, which of course is tangent to that curve at that point, the IROC, the instantaneous rate of change, also known as a derivative. And we see that at x equals 0, the derivative of sine x is 1. Now, I could try and sketch all the way through, but I'm going to skip up to the other major points. You know, we have those 4 points with our trig functions, and I'm going to go up to the maximum, where, of course, I know when you're at a max or a min, your slope is 1. So I know that the derivative of sine x is 0 at pi over 2. Heading back over to pi, or 180, I'm going to draw the little line, and I'm going to try and make it look like the one that we had at x equals 0. When x equals pi, what's the slope? The slope is negative 1. When x equals 270, 3 pi over 2, what's the slope? The slope is 0. When x is 2 pi, it's the same as when x is 0, the slope is 1. So let's trace that out. Oops, sorry, slow drawn. What have I made? I've made another periodic function. And in fact, I've made cosine. And I know that if I continue on this way, what will happen to the IROC, or the derivative? It will continue to cycle just like the function is. So what did I learn? I learned that the derivative of sine x is cosine x. So there we go. Sweet and simple. So if I ever want to find the derivative of a sine function, or sine x, let's keep it simple now, I know it's going to be cosine x. So let's look at these two examples. Here we have the constant in front of the, or the coefficient in front of sine x. So we know that our derivative for sine x will be cosine x. And we just slap 3 back in front. In the second one, same thing. You can think of 2 over 5 as the coefficient. Stays in front. Derivative sine x, cosine x. Let's start the same thing over with cosine. So I see my cosine curve starts at a maximum, goes through 0, down to a minimum, up through 0, back to a maximum, and repeat. So let's think about what the instantaneous rate of change is at all these key points. Point P, they've labeled again for me. I want a fatter pen, hold on. Bear with me. Okay, they've labeled again, and I see that the slope, because we're at that maximum, is 0. When I get to 90 degrees, it's a slope of 1, but it's a slope of -1 because the function is decreasing. There we go. Over to pi, I'm at a minimum. The slope is 0. At 270, the slope is 1. And once again, finishing off at 2 pi, the slope is 0. Let's trace what we've made for our derivative. And continuing on, repeating. What's this? Well, it starts at 0, so it's a sine, but it doesn't go to a maximum, so this is a negative sine. And here we go. We can observe that the derivative of cos x is negative sine x. So when we get down to the two examples, now we're mixing it up. For the first term, and we can break these apart, derive each term separately, just like we could with all of our polynomial functions. I have the coefficient stays the same, and I remember that the derivative of sine x was cosine x. For the second part, I'll write it in separate chunks. We have 3, and the derivative of cosine x is negative sine x. So just clean it up a bit, and you could have, oof, I've left myself no room, I'm going up here, 2 cos x minus 3 sine x. Looking at number 2, we have -1 times cosine x. We know that the derivative of cosine x is negative sine x, so we're going to end up with negative sine x. So just drawing attention to how the signs can really mess with you. And then we have a coefficient -5, and sine x derivative is cosine x. So we end up cleaning that up as well, and it just changes the first term to sine x, and then minus 5 cosine x. Of course, by the time we hit our last topic in differentiation, we know that it's not going to be that simple, that sometimes we need to find the sine of not just plain x, but a function. So if we're looking at the derivative of sine u, where u is a function and not just x, let's think about maybe that we're going to have to think about the chain rule again, and we're going to be looking at cos u du. Same. If we were doing the cosine of a function, suddenly we might be looking at a derivative that is negative sine of that function times the derivative of it. So we're going to go through a few examples here just to kind of understand what the questions are asking and how we go about it. So whenever you see sine squared x, that's how we write it, but what you should think about is this. So here we have an inner function, which is sine x, and an outer function, which is, u squared. So if you wanted to find the derivative of this particular bad Larry, we are going to take the outer function, and we know that we have 2 sine x as the derivative of that, and then of course the inner function sine x has a derivative of cos x. And we'll get more into this in the next few slides. Number 2 is another composite function where our inner function, and you can put assumed brackets there, took out that sign. Our inner function is 2x, and then our outer function is sine u. So for our outer function, we need the derivative of that, which will be cos u. And then we need to have the derivative of the inner function. Derivative of 2x is 2. Put the number in front. 2 cos 2x. And I've added the brackets and kept them because it's cleaner. Number 3 gave us some brackets to clean up, to have. And once again, we have an inner function that is x cubed and then an outer function that is cos u. So for this one, let's switch to red. We are going to find the derivative of the trig function, which will be negative sine x cubed, and then the derivative of u, which will be 3x squared. And suddenly we have negative 3x squared onto sine x cubed. Last one, let's do purple. Ooh, this one. What do we want here? Product rule, right? We've got a nice plain old cos x, and we've got x squared, so I know that the derivative of x squared, and I'm just going to write it below, is 2x. I know that the derivative of cos x is negative sine x, and we're going to apply that product rule where it says that du times v, or u prime v, let's clean it up by writing like that, plus dv times u is a derivative. So 2x cos x, I'm happy with how it's written, but I want to clean up the second term, negative x squared sine x. And I have blasted through that one, but I know you've seen product rule before, and you know that you can just kind of do the this plus this, and it all works out. We've got another couple versions of the chain rule, so let's summarize it with our table. So if we have a function f of x is equal to sine u, fancy wording looks like this. Also easily put down like this, and the same thing. So if you're looking for a sine of a function, here are what the derivatives are going to be. It'll be cos of that function times the derivative of the inner function. So chain rule, composite functions. Here's our cos of a function rule for finding the derivative. And if you're differentiating the powers, we already knew this one. So you should be feeling pretty comfortable with this. Why am I showing you all three? Because we're really going to pile on with the differentiation now. I've called this a warm-up, but it's already pretty terrible. So what do I want to do here? I see cos x times sine of a function. So I want to use the product rule, but I got to do a little bit more work with one of the two parts of it, the v. So I'm just going to write what I usually write and kind of split it in half. I know that the derivative of cos x is negative sine x, and that's fine. The problem is I just have to do a little more work on this side to find the derivative of this. So let's go old school. Let's set u equal to 4x cubed plus 9. And then we also know that our outer function is sine u. So for this, looking at the table or getting your mind wrapped around it, we know that the derivative of sine u is cos u times du. Okay, so we know that that will be cos of 4x cubed plus 9, and we just have to find du from here, and that would have been 12x squared. So there it is, times 12x squared. Now we're ready to do our kitty corner. We know that when we do the first one, we're just adding, so we can go cos x is going to multiply by this. So I'm going to clean it up as we go. We are going to have 12x squared I'm going to put in front, and then, I'm going to put the cos x next, and then I'm going to put the cos of 4x cubed plus 9. There we go. And we know for the other side of our product rule, we do the kitty corners there, and we're going to just have our plus, and which is going to be a minus because of the negative in front of the sign, sine x onto sine of 4x cubed plus 9. Woo! That was the warm-up. These next few slides are going to show you functions that looks kind of the same, but their derivatives are going to be very, very different. So for this first one on the left, what I want to do is rewrite it. I'm going to switch back to black in something that makes a little more sense to me, so that I can see how the different functions are nested. I can see how this composite function looks. So I'm putting the cubed on the outside. We don't only have two functions here. We have three. So let's define them. I'm going to say the innermost one is going to be 4x plus 1. I'm going to call that u. What's the next level of this onion we've got going? Well, it's going to be the sine function. So, you know, whatever, I like the u's and v's, we're going to call it, the v is the sine of u. And we're going to have another one, and I can use y because it was y. I'm going to say y is v cubed. So that cubed. Okay, here we go. So we're going to start with du, just so we have it. And we see that du is 4. Great. And now we have dealt with that function. And we have function v, which is sine u. And we know that the derivative of sine u is cos u times du. So let's put our values back into that. So we had cos, and I look up to my red thing here, and it tells me that u is 4x plus 1 in case I get lost. I always like to leave references there. And I had just found du, so I know it's 4. So that's dv. Great. So keep going. Chain this this rule along. And next we need to find our main derivative, which is dy. And I see that y is v cubed. So I know that the derivative of something like this will be 3v squared, the kind of power one, but multiplied by dv. So go back, find what everything is. So I see that my derivative will now be 3. V was sine u was 4x plus 1. So I'm just replacing all the values. You can do it in more baby steps if that works for you. And then I have to put that square back in. So I have dealt with this. Now, fortunately, I already wrote dv up here nicely for myself. So I'm just going to put that beside it. And I'm going to clean everything up. The 3 is going to multiply with a 4 and make 12. I might put the cos 4x plus 1 first. And then I'm going to deal with this sine 4x plus 1 squared. But the squared's on the outside, so I'm going to write it back in the way people like to write this. Sine squared 4x plus 1. Same. On the right side of the slide, we have this other function that kind of look the same, but once again, very different. So our innermost function, what we're going to call u, is 4x plus 1. I don't care what letters you use. You can use a Christmas tree to represent it. It's just something that you're substituting in so you can wrap your mind around it. This time, instead of going to the sine next as we head outward, we're going to go to this. So we're going to call this function v, which is 4x plus 1, which we called u, and we're going to cube it. And what's our outermost function this time? This bad Larry. And we define this whole thing as v, so let's call this one y because we're already at the outside. I would have used w if I hadn't been done. So we're going to say y is equal to sine of v. Same thing. Start by finding the derivative of your innermost function. du is still 4. Now, go to your next layer. What is the derivative of v? dv, it's a power, is going to be 3u squared, power with a chain rule, du, which I'm going to take numbers and put them back in right now. So I'm going to say it's going to be 3. U was 4x plus 1. I'm looking up. That's why I list them. And then du I had as 4. So once again, 12 onto 4x plus 1 squared. Excellent. And that's where we usually stop. But now we have another layer. So we have to find dy, which is where we want to stop. And we know that the derivative of sine is cosine. So it's going to be cosine of v multiplied by the derivative of v. So let's go back and replace values. So cosine stayed the same. V was u cubed, okay? Let's do this one of steps. Cos u cubed. We can take all day if we need to. And then we're going to multiply that by dv, which we have numbers for already. So let's replace u with 4x plus 1, which is what it is. Cos 4x plus 1 cubed onto 12 times 4x plus 1 squared. And let's clean everything up so it's more readable. Put the 12 in front. Let's put the 4x plus 1 in front as well. Make sure it's squared, and then cosine 4x plus 1 cubed. We have two problems on this slide. I'm going to show both in class, but for the video, I'm just going to do one of them. I'll do g of x, just to give you a hint. If you're trying on your own for f of x, look at what you got. You got a coefficient in disguise. So I would approach this one by first rewriting as this. So that's your hint for that one. All right, let's go with g of x. Now, we could do the same kind of thing and make it into a product rule. We definitely have a function over a function, but let's remember our quotient rule and use that instead. It took me a minute to remember the word quotient. So when I look what I've got here, I see 3x. I know that the derivative of that is 3. And I see cosine of x squared. So a little more complicated, but we can do our same thing. I will just take a little time out and deal with that. Let's say that x squared is u. Then our second thing, let's call it v. And I know I'm using u and v again. Maybe I'll say x squared is w, something different. And v is cos of w. So if I wanted to find dv or v prime, I'm going to take negative sine of w, which was x squared, and multiply it by dw. Took me a minute, which is 2x. All right, and it gives me 2x. Okay, so I'm going to write that over here. V prime is negative 2x sine x squared. Very tight. I'm going to box this stuff off because this was all just to find the derivative of the denominator of this fraction. I'm going to write down over here, in case I forget, what the quotient rule is. U prime v minus v prime u divided by v squared. Okay, so now let's put it all together. We have u prime is 3. V is cos x squared, and I'll be doing all sorts of bracketing. And we're going to subtract v prime, negative 2x sine x squared, and multiply that by u, which is 3, and then divide it by v squared, which would be cos squared x squared. So noticing I'm putting that 2 beside the cos, it could have been on brackets at the outside of the whole term as well. So let's clean it up a bit. 3 cos x squared. I have minus and a minus, so that's going to turn into a plus. I have a 2 and a 3, so I'm going to make it 6. At this point, I'm going to realize I made a mistake, and I forgot to add an x in. U is 3x, du is 3. So cleaning that up, again, I have 2 x's, so I'll have x squared, and then finally sine x squared, and let's put that all over cos squared x squared. And I'm leaving this. On this slide, I'm only going to do one of these, I think. Maybe I'll do J, but the thing is now we are really piling on. So I'll leave H for class. I'm going to rewrite, I'll just kind of cross it off for now so we don't get distracted. I'm going to rewrite j of x in a way that makes everything that is happening more clear to me. Not sure how that's going to happen. I have cosine of, I'm going to leave some space, a power with another power inside. And I think that's enough brackets. Nope, I need more brackets. I need this bad Larry. There we go. That's terrible. Let's define our variables. Innermost in this hot, hot mess, u is x cubed. Next is a sine. V is sine of u. Next is a square. W is v squared. And finally, we have a cosine. And we're up to our answer. Cosine w. Starting from the middle, du is 3x squared. Now, if v is sine u, dv is going to be cosine u du. And I'm going to replace those with letters, or the x's, cosine x cubed multiplied by 3x squared. I'll leave it out of order for now because I know I'm just building on, and I should make this look more like a v. That's dv. Next, I'm going to go up to w dw. If w is v squared, dw is 2v dv. Okay. V is sine u, and dv, and I'm going to start to rearrange it a little nicer, but still not super nice. 3x squared cos x cubed. Okay, so let's clean that one up one more time. I'm going to highlight a bit this stuff and put it in front to put it together. So I'm going to have 6x squared onto sine, and I'm going to replace a u with the x cubed, onto cos x cubed. And some superfluous brackets there, but I'm just trying to be careful. Okay, now we're ready to go to our last step. We want the derivative of our original function j, which we know is cos, the j was cos w when we did all the substitution, so the derivative of cos is negative sine w multiplied by the derivative of w. We've got that already. I'm just going to give it a little highlight. Whoa, that is not a highlight, that is a cross out. Definitely don't want to cross that out. Let's try and get a highlighter. There we go. So I know this goes here, and I've just got to mess around getting my other part back. So negative sine of v squared. And I'm just dealing only with the negative sine w to get it back up to where I need it to be, equals negative sine of sine squared u, or sine u with the brackets all the way around and sine, equals negative sine of sine squared x cubed. Good Lord. Okay, so that was just me dealing with this part. So I've got that half, and now I have to multiply pink and blue together. So I have to smash these bad Larrys together. So just taking a pause. What can I put in front? Pink negative, blue 6x squared. Oh. I'm going to write sine x cubed cos x cubed next. And then I'm going to deal, and I'm going to run out of room. It's so bad. I'm going to deal with the sine of sine stuff here onto sine of sine squared x cubed brackety bracket bracket. There you go. That is dj with respect to x. Ugh. So that is it. That is the last example for this video on trig differentiation. Ended terribly, but you know, if you can wrap your mind around what's happening, you're doing great. I would definitely watch the video with lots of pausing and staring, and hopefully it works itself out for you.